Good morning, everybody. Very good. Looks like a lot of energy today also. It's a third day. We are all kicking and ready to discuss more. Uh, Last 2 days, we talked a lot about mechanical properties, elastic properties, viscous properties, viscoelastic properties. Today, our focus is going to be on dairy products. When I say dairy products, not only dairy products, any solid material, semi-solid material will fall into that. It's not more specific to the dairy products, but somehow when we developed this course 3 years or 4 years ago, there I don't know what thought went into ourselves. So we put dairy in every lecture today. But whatever we are going to discuss today, it will be applicable to any food material for that matter. It's not specifically for only dairy only. I just want to repeat that on Friday we will have a practical demonstration also. So that will give you a lot more opportunity to really see the application of whatever material we are discussing in this workshop. I think that timing is more important, so please make sure that you put it in your schedule so that you will be there on Friday morning, maybe hour and a half or something like that. Any questions anybody has at this time before we move on? Hearing none, I just want to give you some missing information, or I didn't put this information in more elaborative or more with the examples. So this is what we talked about yesterday morning, where we looked at the characterization of fluids. There are Newtonian fluids which has constant viscosity. Shear stress is directly proportional to shear rate. So it is the straight line. If you take the slope of that line, that is viscosity. So wherever you take the slope, the slope is still same. No matter whether doing it here, do it here, do it here, do it here, do it here, right? That is why the fluids obey like this. They are Newtonian fluids. The typical example is water, oil. Obviously, when you compare viscosity of water, which will be less than the viscosity of oil because of the thickness of the material. Oil is more thicker, water is less thick, so oil will have a higher viscosity than the water. Make sense? Okay. And then while discussing things yesterday, Madam Anitita asked me about why these fluids are, some of the fluids are called shear thickening, some of them are shear thinning. What makes them to be like that? I answered yesterday that I do not know, but I went home and then I checked the reasoning for that. The shear thinning fluid, which are pseudoplastic, initially it is harder to shear, and then once you increase the shear rate, if you shear them faster and faster, it is easier to shear. That's why it's called shear thickening. The reason behind that is there are molecular structures, they are tied together in this fluid. So initially it is harder to shear. So when you keep shearing them, increasing the shear rate, you are breaking those molecular structure and it become loosen up. So those molecular structure is loosen up, so it's become easier to shear. And then when you come back, they come back to the same trend. At a higher shear rate, the molecular structure is getting loosened up. As you decrease the shear rate, speed at which we rotate, the molecular structure it coagulate again, it has become tougher, it's become stronger bonding, so it is harder to shear at lower shear rate. Okay, that is the reasoning behind it. I'm not sure how much it is true. This is the information I got from Google search. I think it makes sense to me. That could be the reason. That's the only reason. And then for shear thickening, what happens is initially at lower shear rate, the suspension of whatever fluid you have, uh, it, it has a volume. When you increase the shear rate, volume get increased. There is foaming forming or pore spaces forming, volume get increased. When volume get increased, it become harder to shear for a given material. The amount of material is still same, nothing changed, but because of the shearing action, the molecules get disintegrated, and then more air spaces, pore spaces forming inside, that creates the higher viscosity. So that is the reasoning I got. I mean, when I looked at it, it looked to me that I am convinced that that would be the right approach. I mean, the right reasoning. Okay, and then I have a example here. I am missing that madam. Hopefully, she will be here soon. She asked me. I didn't have example for Pingham pseudoplastic. What would be the good example for the Pingham pseudoplastic? Literature tells me that peanut butter is the Pingham pseudoplastic. What it is basically there is a yield stress. If you shear the peanut butter, there is a yield stress, and then after getting the yield stress, the peanut butter becomes shear thinning fluid, similar to pseudoplastic. Okay, does it make sense? Okay, I have a question for you all. Is mayonnaise is a shear thinning or mayonnaise is a Pingham plastic?
Actually, in previous yesterday's demonstration, we got the graph almost like there was a yield stress actually, and that was making it Bingham plastic like features. But I don't know the exact reason or the exact thing. What is it happening?
It is Bingham pseudoplastic.
In yesterday's demonstration, you saw yield stress for the mayonnaise. If we get a yield stress, then it should be Pingham plastic. You cannot forget the yield stress. Sometimes we tend to not to worry about it, and then they may tend to show a shear thinning. But once they achieve the shear stress, yield stress, they should be like a Newtonian fluid. Another way to test them is sensory wise. If you have a bread and then you put mayonnaise, once you pour the mayonnaise, that will be like a lumping is there. So you need to force it so that you can spread it out. So when the force you apply, that's yield stress. And then you spread it out, it's become Newtonian. Make sense? But when you do the actual test, it may look like it's shear thinning, but it's not shear thinning. It can be shear thinning only if there is no yield stress. If you see a yield stress, then it will not be this type of fluid, but that will be this type of fluid. Follow me? Do you agree? Do you all agree with that? Okay, that's what it is. So there are a lot of things out in the Google and the literature and all. You have to find the right source to get the right information. So just not only one source will give you all the information you need. And also you want to be more critical of the information you get. Make sure that you understand the material and consult with other people, and you get the right information. That's more important. Madam, you asked me about the example problem. Example for Pingham pseudoplastic, that is peanut butter. The question here is from Nivedita. Does it depends upon the concentration of your sample? Are you talking about mayonnaise or?
Any normal material. For example, if it is starch, if it is having a higher concentration, it will be more thicker, and if it is a lower concentration, it will be less thicker. So if it is more thick material, then it behaves as bingham. Is my assumption. I'm not really sure, so I'm just asking whether it depends on the concentration also.
I agree with you, Nivedita. It could be, it depends upon the concentration, but the bottom line is when you do this kind of characterization work, you want to make sure that you have multiple replications, 3 times, 5 times like that, and make sure that you every time you get the same characteristic. If as long as you follow that, then you are good to go. But in terms of mayonnaise case, that cannot be true because mayonnaise is mayonnaise, right? As long as you take the same brand and do 3 or 5 times of test, and then every time you do that, you get the same characterization, then you need to account for the yield stress, and that is pink and plastic. Okay, now we are going to talk about texture profile analysis. Basically, again, it's a texture, but we are analyzing the profile of this texture. On Monday, we stopped our discussion up to this point. This is where we did. We just did the compression test, and our compression test results, not the compression test results. I mean, the output we got was not this nice, right? Why is not? Why is the case? Okay, I'm going to show you again here. On Monday, whatever we discussed, we had this kind of curve. Let's say stress, strain. So here I don't see any fracture or rupture, anything like that. I see fracture here, bio yield point, and rupture like that, right? So what is the difference between this curve and this curve? Any thoughts? Ma'am? This sample probably did not have a rupture. That's one way to think about it.
Maybe it's a uniform sample, like the surface is uniform.
Surface is uniform. That could be the reason. Any other thoughts? Sample is not brittle. Sample is not brittle. Okay. What is the characteristics of brittle sample? Yeah, the brittle sample play a role only if you break it or you extend it, not in the compression. You will not able to know in compression test whether the sample is brittle or not. Agree with me? Okay, so that may not be the case. What else? Another hint I can give you is when you go up to this rupture point, how much deformation we are giving for the sample. Any idea? No, how much deformation, how much deformation we are giving to the sample. No, okay, set value. The answer is set value. What is the set value? That's what I'm asking you. Okay, what is the sample size here? Okay, 20 mm sample, assume that is cylindrical, so 20 mm. So how much deformation we are doing in this test? 10 mm. 4 mm, okay. 4 mm out of 20 mm, 20% deformation, right? 10 mm out of 20 mm, 50% deformation. Do you think if you do 50% compression, will it rupture? It will not rupture. You have to do at least 80% deformation so that this will go all the way down and you will get the rupture. In texture profile analysis, you cannot even think about going more than 30% or 40% deformation. because once it ruptures, you don't get the profile. Make sense? If it ruptures, then when you release it back, you don't get this kind of nice profile. So usually I tell people that don't go more than 30% deformation. So what it means is, if you have a 20 millimeter height sample, so if you do less than 10 mm going down, not even 10 mm, 5 mm, 4 mm, 6 mm like that, then it will go down and then come back, go down, come back like that. Then you can be arguing with me, Muthu, then it's not really a actual double bite, right? If you bite it, you are rupturing the sample. Then you are done with that, right? Then you are massaging it again and again, so that until it becomes ready to swallow, then you are swallowing it, right? So this is not actually seeing what is happening in terms of sensory analysis. This is something related to the how to characterize your sample. That's all about it. I'm not sure how many of you remember this texture profile analysis. Yesterday when we talked about, I said this is a subjective test. It is not objective test. Follow me? Because we are not doing any stress and strain information here. All we are doing is we are monitoring a force with respect to time. That's all we are doing. And we are trying to mimic what the consumer may do it. Just as if they are slowly biting, let it go, bite, let it go like that. But that is not actually happening. So what is the purpose of doing this? I do not know. I have, my student and myself has published some work in the same area. We have done a lot of texture profile analysis, but it's primarily my student thought they have to do texture profile analysis. I said, go ahead and do it. All I know is from this test, the peak force. I know for sure if the sample is harder, hardness value will be higher compared to softer sample. Everything else is just a mimic. My personal opinion. I am not sure how much you want to take it. You can decide yourself, but that's why I said it's a subjective test. It may not. It will be objective test if it is done correctly and the hardness value only. And because I know that if I do instrument test and then ask Nivedita to do the same thing, and then she will give me the similar hardness characterization. She will, if I give her 2 samples, and then same 2 samples, if I do this compression test, low compression, I will get the similar result. And if she gives me it's a sample 1, S1, S2, and then this is S1 sample, and then S2 sample is like here. So S1 is higher, S2 is lower. She will give me the same information. She will say S1 is harder, S2 is softer. That's all she can tell me. But instrument, I can tell you how many newtons force is there. She cannot tell me how many Newton force is there. Or I cannot tell this. I mean, I'm not complaining Nivedita. Myself, I cannot even tell how many Newton force I am applying. Right? Even though I am a scientist, I cannot tell because I don't know. I don't have a load cell sitting in my teeth where my load cell tell me this is what you are experiencing, right? I'm trying to have some fun here so that it's not all about science, it's also thinking process, right? So that's where it is. So at least you guys understand what I'm coming here. So when you do texture profile analysis, You are welcome to do that. I have no problem with that. But make sure that you don't damage the sample. Once you damage the sample, don't continue to do the sample. You need to reduce your deformation so that you will get the profile like that. Only if you get the profile like that, then there is some meaningful information you can obtain. But still, it's not objective test. Because what you are going to get is force and time or force and deformation. This cannot be converted into force and stress and strain, because it's not only loading, it's also unloading. You cannot get the strain value there. Only if it is keep on loading stuff, then you know how far down it went, and then you can get it. Otherwise, if you try to convert this into strain value, it will get messy. You will not get the profile like this. In fact, if you do the compression test, texture profile analysis test, actual curve will be this is how it will look like actual data curve. You will not get a nice graph like this. The software does all the thing in the background, and then it will show you like this. Raw data will be like this. If you plot the raw data, that will be like that, not like this. It takes more time to convert this into this one. But software does it in the background, so you don't see what is happening in the background. But today's discussion, we are going to see what's going to happen, how these things are calculated. Any questions on this? Yes, Nivedita, please. Nivedita has a question.
Sir, if it is a cake which is softer, it will give a good profile like this. If it is a solid product, like extruded product, it will be brittle also. So the first bite itself it will break. We won't get the second profile properly. So is it advisable to do for brittle substances also?
It's not. I will not do that. That's what I'm saying. If you don't get a profile like this, don't even think about spending your time. Yes, you are wasting your time, because you are not going to get any meaningful information. Because it's a crumbly one, it's brittle, you are going to break it and it won't come back, anything coming up. And then next bite also you cannot do anything. Right? Next, there's no, you are not going to even apply any force into it, because there's no material to apply force. Once it's crumbled, done deal. So if you have extruded product, don't even think about doing the TPA, because TPA is not for everything. It's not only TPA is the end of the world. That's what I'm trying to tell. If you have extruded product, put it in the 3-point bend test, and then cut it. You get one value, that's hardness value. Life is good. And you may be wondering, Muthu, what is this? I get only one data. How do I publish this work? What is going to tell me, right? You have to try other things. Don't even think about doing the. I don't know. People are publishing it apparently, but it's not coming to me. So I probably reject it immediately. But that's me. So, but as a scientist, you have to see what is good for you, and then you do what is right for you. As long as people publish it, so be it, right? Nivedita has a question. Very good question. I do not know. All you can get is only hardness value, in my opinion.
Now there can be like crispiness work, number of fractures divided by how much was the piece, what was the work done. Depending on that, we can get the crispiness work. So
it all depends upon what is your definition of whatever you are trying to measure. If you define it correctly, and then you follow the right process, that's all it matters. And then even crispiness or crunchiness. What's the difference between crispiness and crunchiness? Nivedita is telling me you are talking about brittleness? No.
It's similar.
It is similar, yeah, that's what I'm saying. how well we can differentiate between those two. Uh, we are talking about two different terms here, right? Crunchiness and crispiness. Yes, sir.
We make in home papad.
Yeah.
So papad is kind of like a flat and a little less elevation. So when we eat that bite, it is like a crunchy. And when we go for a like voluminous product of expanded snacks or puffs, then that we bite, it is maybe like crispy.
Yeah, but those are all sensory terms. How do you measure this instrumentally? I think that is what Niveta want to know, right? If it is extruded product or chips like that, how can I get more information about that in instrument wise? That's $1 million question. If I find something, I will communicate with you guys because I'm not working in that area. So if I find something, I will let you know. But there is a lot of sensory analysis people can do it, but that won't be objective test. It will be a subjective test. Each person will have a different answers. As long as the same person is doing that, trained people doing that, there could be truth to it. But at the end of the day, as an engineer, a scientist, we like to see numbers with the meaningful units so that we can appreciate the value of those numbers. Otherwise, if it's a sensory person, I'm going to say number 5, number 4, number 3, number 1. If it is 5-point scale, if it's a 9-point scale, 9, 7, 6, 7, like that, randomly it's going to go, and then an average comes out. When you do statistical analysis, you cannot have a statistical significance. So what is the point of doing that, So in scientific terms, I'm saying, if it's a product development, which is okay, that's what consumers are going to do. You just follow the consumer trend, preference, and at the end of the day, they want to make money, right? Industry want to make money. People are eating food. They have to pay for it. They have to make money. So sooner they get money, it's better for them. Sir?
If we are going to test in a dry form as we get, that may be called like crispiness. And when we go for that bowl-like texture, so that's when we get maybe called a crunchiness.
Everything is fine. I totally agree with your all your responses. My only problem is, can you give me some number, some quantification, where this much force you are applying, this is what it is, like that, which is not possible. Nivedita?
So if in case of crispiness, if once the hardness, if you are testing the sample, when the probe hits the sample and it crushes, there will be a different number of peaks. Can we count that peaks as the crispiness? It was
You can count, yeah. What Nivedita is saying that is, when you have the sample with you and then you do the texture profile analysis, and then it's going to give you a lot of peaks and valleys, sinusoidal way going up and down like that, and then you're going to get to some peaks like this. Can you count the peaks and then report that? Yeah, but again, how many peaks you are going to report that? How you are going to count everything? At the end of the day, you are going to say, I got 30 peaks here, more energy I input, and then I put 20 peaks for the other sample, less energy input. That's what you are going to tell me. You are not going to give me any quantification number.
gives the data to count the number of peaks. I get the graph and I tell the software I need from this area to this area. What is the number of peaks from it? From that, I am trying to tell that this is more crispier and this is less.
But again, you are talking about number of peaks only. But there is no information about how much energy you put in and things like that. If you can give me some total energy input, this much joules per meter cube like that, then I agree with that. That's objective test. If I'm going to get to only the peaks and things like that, I don't even know the value of what is the width of the peak, what total energy input is. So those are the things you may want to think about that, That's what I think. I'm thinking, Looks to me we are running late for today's section. I thought we will have a lot of time, but it's okay. I mean, it's what it is. I told you also, it's not about how much material I want to dump on you. It's how much discussion we have and how much we are learning together. So, more the merrier. So I mean, sometimes I come with less amount of material and then they ask me, can you extend your presentation another 10 minutes? Then I am scratching my head. I mean, whatever we are discussing, they will cut it off, so don't worry. So it's all about show recording, and then director takes care of all the editing and everything else. So as long as, I mean, I am here to have fun, and I want to make sure that you are also part of the discussion. You are also learning something. So otherwise, it will be a very set presentation file, set dialogue, set description, and no interaction. That's not wanted in a learning environment. In fact, I don't like this setup at all, to tell you the truth. This style, it's a distance. I don't like to keep a distance. I like to go move around, talk to the people, and say how they are doing and stuff like that, see whether they are understanding stuff. When they do calculations, I move around the people and look after the shoulder and see whether they are doing the calculation correctly or not. That's the only way they can learn, right? Otherwise, you will be fooling me, I will be fooling you. Then there's no learning, right? And then you won't want to come to class at all next day. Or you come here and then you doze out and you attend the cell phone and chat, things like that, right? So, okay, let's move on. So actual graph is, this is what you get from the texture profile analysis. This is one of the example I have you. This is the actual software output you get. There are several information you can collect from this type of texture profiles test. So basically what it is you are loading the sample, you are compressing it, or first compression is this. There are some, this type of yield may occur, but it's not this will not happen for all the samples. Some samples will show you a little bit of this, not all the samples will show you this. So it's called fracturability. So there is some internal structure collapse, and that's what you see it here. And it is ingredients to the sample itself. It's not just a behavior, it's just a microscopic failure inside the sample. And that will come to you while you are doing the test. And this is the maximum force, it's called hardness. And this is the first compression, and this is the first decompression. Withdrawal, when you remove the probe, this will go down. For all the materials, for all the viscoelastic material, the area under this curve should be less than area under this curve. If it is purely elastic material, this curve and this curve should be the same, because it has to come back to the original thing. It has to be same. Because of the viscoelastic material, this is less energy recovered, more energy input. And then there could be some material sticking to the probe when you release, when you rest it out, and again you are compressing it, and then decompression. The second value peak will always should be less than the first peak. This cannot be more than this, because some energy is lost, then the second peak will be less than the first peak. And we don't care about the second peak at all, because we decompressed it, so this may not have any meaning to it. And then second withdrawal, second decompression. And if you want, you can get many peaks and it get messy. Then how do you compare these? What is whatever comparison you try to do, what is the meaning of it? What is that going to do for you? So far so good. So we can get a fracturability, we can get a hardness value, and then area under this curve, from this curve to from decompression area and then compression area, ratio of that will give you the cohesiveness. Did I say that correctly? It's not even here. Okay, I will show you in the next slide. The adhesiveness is A3. This is the area under the adhesiveness, and then so we'll go one by one here. Not all products fracture, but when they do fracture, the fracturability point occurs like here. That's what we are talking about here. It's a first compression of the product. After that, you won't get anything. If you don't get it here, you won't get it in the future peak, future bite and all. If at all happens, it happens first bite. A lot of times it won't happen at all. You have to do really much more higher deformation. If you do a higher deformation, you don't get the profile like this. So it's up to you how far you want to go and what kind of data you want to collect. Hardness value is the peak first compression of the product. The hardness need not occur at the point of deepest compression, although it typically does for the most products. What it means is, if you compress it 30%, 40%, definitely you get the hardness. So the next property is cohesiveness, how well product withstand a second deformation related to its behavior under the first deformation. It's measured at the area of during the second deformation divided by the area of work under the first compression. The second compression is here, and this is first compression. So this area over this area is the cohesiveness. Or you can also say length 2, length 2 or length 1 is springiness. So this area under this curve divided by area under this curve. Springiness, how well the sample spring back after it has been deformed during first decompression, first compression. So if you second compression, this is length 2 deformation, first compression length 1 is deformation. So length 2 to length 1, that dictates the springiness. Typically springiness will be less than 100% because viscoelastic material. Yes, elastic material, springiness will be 1. So your number should be 0 to 1 or 0 to 100%. Another property is gumminess. Primarily this type of measurement is only good for the semi-solid products. Cheese, what else can we think of semi-solid food? Gels, yep, gels. So those things will play a role. I mean, they can be, you can measure the gumminess for this product, which is nothing but the area 2 under the area 1. The chewiness is basically gumminess times springiness. Springiness is again length 2 over length 1. So chewiness is the gumminess times springiness. And then finally the resilience is the how well the product fight back to its original position. So area 5 over area 4 is resilience. If it is elastic material, 100% resilience. So area 5 will be the same as area 4. That's how you get it. Any questions on these characteristics? Okay, time for doing some homework. I think I mentioned to you also, you will get all the presentation files we are discussing. You will get a flash drive on Friday morning after the practical demonstration, and you will get all these presentation files, and you will also get some reading material. I have a couple of books, e-books, that will be loaded in the flash drive, so you can use it for your references down the road. Okay, the resilience is nothing but the how much area under the curve, then area, when I say area, energy, let's talk about the energy. Area under the curve is nothing but the energy input, energy recovered. So resilience is nothing but the how much energy recovered divided by the how much energy put in. So this is area under the curve during decompression, area under the curve or energy recovered during decompression divided by the energy input during the compression. That is called resilience. Okay, what was the other one? The springiness. The springiness is basically how well the product spring back between the second compression and the first compression. If it is elastic material, there will be 100% springiness. Right? Spring, you load the spring, release the spring, load the spring, release the spring. The crafts will be the same. How many times you compress, decompress, doesn't matter. Questions? You have to take this information with a grain of salt in the first place. Because that's why I said that I don't believe in this, in the way of analyzing this way. All I believe is only hardness. Because you cannot really repeat the test until otherwise you maintain everything concretely, saying that 20% deformation like that. If you change the deformation, all the values are going to be different. Right? Because if you do, instead of 20% deformation, if you do 30% deformation, your values will be higher. 40% deformation value will be much higher. So what is that meaning? Right? So, yeah.
So what is the basic difference between the springiness and gumminess? If we take in the respect of sensory,
Yep.
then what is the basic difference between springiness and gumminess?
Okay. The springiness is basically, springiness is all about the deformation change. How much material is deforming in the first bite and how much material is deforming in the second bite. So length 2 by length 1 is springiness. Deformation 2 divided by deformation 1. Why deformation 2 by deformation 1? Primarily because that's the only way you can have maximum of 100% of something. If you do by area length 1 by length 2, definitely you will get more than 1. No matter what you try to do. Right? And that number you cannot really explain what is that number means. If you do length 2 by length 1, then it will be less than 100% always, because viscoelastic material. Okay. Now your next question is, what is different? Another is gumminess. Yeah. Gumminess is nothing but the area 2 over area 1, and then you are multiplying by hardness, so that you have some meaningful information. So area 2 by area 1 will be unitless, and then you multiply by hardness, you get a Newton. Newton, that's all, Newton. At least you have Newton there, right? Hardness is in Newton, because that's what the force is, Newton, right? So you get a Newton unit.
So the area under the curve, that means the
It's a ratio of area, so unit cancels out, right?
and then hardness,
Hardness is in Newton.
only Newton, not Newton meter.
Only Newton. The area 2 is Newton millimeter. Area 1 is Newton millimeter. Things cancel out. So you get the Newton. That's why at the beginning I said I don't believe this data. I'm sorry to say that I should not say this in public, but it's what I mean, we all need to speak our mind, right? Otherwise, what's the point in teaching something to students and then forcing them to believe that this is what it is? I'm not trying to change any of your viewpoint here. Your viewpoint is your viewpoint. My viewpoint is my viewpoint. In fact, I told you for the first day itself, When you say I am the expert, I am not the expert. It's not my publications, it's not my whatever awards I received. It's not because of me, it's because of my students only. My PhDs, my undergraduate students, master students, visiting scholars. If it is only me, I'll be like you only forever. I mean, like a student. I mean, you are all individual thing, right? You don't get credit from other people's work. I was in the same boat too. I'm not something different, right? So I mean, there's always scope. Scope is there. So don't think about that. Okay, Muthu is great. No, Muthu is not great. Greatness come from the people who work on for me, right? So you will be a great person also one day. It's just a matter of time. So you just need to give the credit to the people who deserve it. So that's what I'm saying. Okay, where we are going now? I mean, is it clear now? Springiness, comminess. Okay. So we are going to do some homework here. I'm going to pause here. So we are going to do this. There are two samples I have given you, two different profiles here, and we are going to collect this information for both the sample, and then we are going to do the calculations and find out how different they are. Obviously, they are different just by looking at it. Visually, when you look at it, they are different. How much different they are, that's what you are going to do calculations. You can follow me. If I make a mistake, shout at me saying that Muthu, that's wrong number. This is the right number. So what the unit are going to be, so again the issue here is my problem here is we have millimeter, you have Newton, should be meter, right? I keep the millimeter because it's a small number. If I convert that to millimeter, then it becomes 1,000 times less number, and these numbers become very small number. I like to give a bigger number so that we can compare something, Instead of saying 0.001, I can say it is 10, 100, like that. So that's our thinking will be, you will visualize the number, you will see the difference very clearly. If I say 0.001 and 0.0011, no big deal. 10 and 11, that's a big deal, right? So length 1 millimeter, sample A, basically this is the point for the first sample A, so it is 2 millimeter, and then for the sample B, 1.5, 1 is here, 2 is here, 1.5, and then length 2 is here 6, 4, 2, 1.5. So far so good, right? Because this is 4, 5.5, 1.5, area 1. Okay, we need to calculate the area 2, area 3, area 4. Okay, area 2 for the B is sample B is 0. Area 3 for the sample A is half of this thingamajigger. This is 50, 25. Okay, I'm writing it in a different place here. Oh, perfect. Now we got this one. A3 is done. This is A4, A5. Okay, this is A4. So it is 2, which is 1, and then 600. I am approximating here. I'm taking this as a triangle, proper triangle, which may not be right. So this is half, 600, 300. A5 is 300. A4 is here, half, 0.75, 150, 150, 150 times 1.5, 225. Am I doing it correctly? Yes? Yes or no? Okay. Now we got these things and we have to get the area 1 and area 2. Area 1 is whole thing, area 2 is this whole thing. So we do the area 2 first. So this is 3, this is 400, 400 times 3, 1200, half of it is 600. This is 3, 1800, half of it 900. This is area 2, 3, 200, 600, 300. 300, 3, 900, 450. Did somebody write this number somewhere? You are writing it down? Please, somebody write it down because you need to tell me when I go to the next page, I can enter this information. When I created this sheet, I thought I can copy and paste it to the next one. That is not going to happen. Is all the numbers are correct? Okay.
Area 1 of sample B is equal to area 4 plus area 5.
Oh, area 1 is, yeah. It's not adding up? Where did I make a mistake? A4, 1.5, 100, 150. Huh? Correct only? But why they are not adding up? Correct. That's what same thing they were trying. But this one we put 450. It's only 375 coming, so my calculation is not right somewhere. Yeah, I know, but we have to approximate every time, right, correctly. Let me think about it. Sample B is the pink color. Area 4 is this. So 300, 1.5, 300, 1.5, 450, 225, correct போட்டிருக்கேன். And then this is 150, 1.5. Yeah, that's yeah. I keep thinking that, and then I didn't approximate correctly. Right? Because when I calculated this one, I didn't go this far. I went up to this point only. That's why that is small number. So now it's correct, right? Things are rounding up. Okay. Yes, ma'am. Yes, sir.
Please
Repeat area 4. How did I got the number? Okay. All I did was approximation to the core. Approximation to the core. Your software will not do the same mistake. It will go and find each and every every square, and then it will count like that. Okay. Area 4 is nothing but this area. And this is area 5. So what I did was took this height value, width value divided by 2. So that's what I got 225. And then same thing I got here 225. Here same thing here, height and the width 600 times 2, 1200, half of it 600. Same thing here. All is well? Okay, we are in the business. Somebody is going to give me the numbers, right? I cannot remember all the numbers. So length 1 is 2. This is 2. This is 1.5. This is 1.5. Oh, still sitting there. Okay. I was not sure it's going to sit there or not. 900. 450, 300. This is 0, I know for sure. 25, 600, 300, 225, 225. Okay, we are in business. We are getting there. Fracturability is, nope, I cannot say fracturability is 0. There should be some number. 450. This is 0. Hardness is 600 and 300. Cohesiveness is A2 by A1. 600 over 900, 2 by 3. A2 by 1, 3, 4, 450. Springiness is 1, 1. No. 100. Thank you, Nivedita. Gumminess is cohesiveness times the hardness. Cohesiveness this much. Hardness is this much. Springiness times gumminess. Okay, this is what we got. Sample A is much harder than sample B, obviously. Sample A had a fracture probability, sample B did not have any fractures. Cohesiveness is both same, and then gumminess is 2 times higher than sample A has 2 times higher than sample B. Same thing with the chewiness, because gumminess is like that, springiness is same value, and then resilience is 50% for the sample A, 100% for the sample B. This is part of the exam 1. So they do this work during their exam. It's open book exam. Whatever we did now. So yes.
Means sample B is completely elastic, since resilience is 100%.
Yeah, you can say that. Yep. That's a good observation. Yeah, I mean that's what we did. I forced it like that, so it's not really it's not a real it's not a real data. It's a made up data, so that people can think about that and then they can answer me what it means. Because we tend to rely upon computers these days, we don't do any work ourselves. I mean, there is an understatement. I didn't mean to hurt you at all, but what I meant to say is, we have to make sure that whatever we are getting is the right thing we are getting. As much as possible, we have to check it out whether we are really getting the right information, and whether we are really telling the right information to the people.